All right, here's section 11.2, vectors and application of vectors. Definitions. Scalar. A scalar is a physical quantity that only has magnitude or size. A vector is physical quantity that has both magnitude or size and direction. So out of these topics down below, what's a scalar? What's a vector? So temperature, well, that's a scalar. Speed, scalar value. Both of these have a quantity, but they don't tell you direction. Velocity will be a vector. Acceleration, vector. Both of these gives you some kind of magnitude, and they give you a direction of where they're going. The next two, this can be kind of confusing. Mass is technically a scalar. And the reason for that, mass does not include gravity, where the word weight does include gravity. So gravity is the direction pulling you back, if you will, to Earth. Volume, scalar. Force, vector. These two, distance and displacement, they kind of mean the same thing. Distance is scalar because there is no direction. Displacement is a vector because it's the distance and the direction that you're going. All right, notation of a vector. Kind of looks like that old geometry ray, except there's no point B out here. Point B is actually right at the tip of the arrow. So we can call our notation vector AB, or notice the difference at the top. Some people will allow you to use that ray. Some people use half an arrow. This is called a directed line segment. That's our vector. All right, it is not a ray. A ray starts at A, same concept, initial point A, goes through the point B forever in that direction, whereas a directed line segment means it's going to stop. The terminal point, like we said, is at the tip of the arrow. You can also use the following notation. Because mathematicians are lazy, we don't want to use two letters. You might start using U's, W's, and V's are the most common variables to use for vectors, but notice they will bold that variable. If they don't bold it, then they put the arrows above it. We also have a special directed line segment or vector called the zero vector. The zero vector has no magnitude. Its length is zero, which is kind of weird because then what direction is it going in? But we have to have a zero vector because we are going to add vectors. And whenever you want to add or subtract something, you have to have a value of zero that when you add to it, you don't change its value. All right. I believe we call that the additive identity. So if you think about back in algebra, if you had 5 plus 0, that's the additive identity, so you don't change its value. We also have one for multiplication, multiplying by 1, 5 times 1, that's the multiplicative identity. So if you want to call this, this will be our vector identity, if you will, for adding or subtracting. Next, we have notation. You have double absolute value bars or single absolute value bars. I honestly prefer the second one because this represents magnitude, and I don't want you to think that, oh, this is the absolute value and you're looking for a value. Here, it's the distance, so we got to use the distance formula for this and turn it into a positive answer. So it's the length or magnitude. Two vectors are equivalent if they have the same length or magnitude, right there, and the same direction, which, if you want, right below here, put slope. Working definition. Connect all vectors with a terminal point to an initial point. The resultant vector goes from the first initial point to the last terminal point. This is when you want to combine vectors together. So, for example, here's particle A, a particle starting at A, moving to B. Now it wants to change directions and head towards point C. So technically, this is the geographic representation, which we'll talk in the next slide, for adding two vectors together. So if I go from the initial point to the final terminal point, this is our displacement from point A to point C. So vector AB plus vector BC is equal to vector AC. This is called the resultant vector in red here. So if I had these two vectors, and again, I wanted to use now that geometric definition that we just did, and I want to come up with the sum of u plus v, one of the ways I can do that is with the triangular law, which is kind of what we did right here. We built a triangle. So here's vector uv. Notice from the initial point to terminal point, look at the slope, up 2, right 5. So up 2, right 5. Those are the same two vectors. Then we take vector v from that terminal point. It has a slope of positive 3 over 1. Up 3, right 1, there's v. Build the triangle. That's the u plus v. That's your resultant vector. Another way to do this is called the parallelogram law. Now, the nice thing about this is that it's going to justify the commutative property of addition. So here, what you do with your two vectors is you draw both vectors sharing the same initial point. So let's draw vector u. There it is, from that initial point, up 2, right 5. From the same initial point, let's do vector v, up 3, right 1. And now we build a parallelogram, which means from v, you're going to have opposite side. Here's going to be my u, up 2, right 5. And from v, the tip of v, we're going to go up 3, right 1. So we build a parallelogram. Now, what to connect is the same initial points where they're sharing the initial point to where they're sharing the terminal point. That is going to be my u plus v. But notice also, if you use the triangle law, this is v plus u. So that proves that vector addition is commutative. So u plus v is always from the shared initial to the shared terminal. Definition of scalar multiplication. So if you have a value of c, that's a constant, and a vector v, we multiply the two together. The only thing c will do, it's going to change the length by the absolute value of c, being multiplied to the length of the vector. So let's say we have vector v. That's up 3 to the right 1. If I want to draw 2v, then what do? Is I need to double this distance or double the slopes. Instead of up 3, right 1, I would go up 6, right 2. Up 6, right 2. If I wanted to do half of v, okay, I'll go, instead of up 3, right 1, I'll go up 1.5 to the right 1/2. You're basically cutting the slope values in half. If I want to do negative v, everything's in reverse. I multiply negative 1. Instead of going up 3, right 1, now I go down 3, left 1. So when you multiply by a negative, that means the vector is going to go in its opposite direction. If I want to do negative 1.5v, again, pick a point. I'll go down 3 times negative 1.5, negative 4.5, and then we'll go, boom, to the left, negative 1.5. So scalars make vectors larger, smaller, and change their directions. The difference of two vectors, u minus v, can also be written as u plus a negative v. So that's how we take care of subtraction, by turning it into an addition and multiplying the second vector by a negative. So if I want to do u minus v by the triangle law and parallelogram law, so we're going to make this a negative v, so change it in its opposite direction. There we go. Triangle law, start with vector u, and now attach negative v to it. So we're starting here, we're going up 3 to the left 2. And then make your triangle to build that resultant vector, and there's u minus v. If we did the parallelogram rule, bring in your u, bring in your v, but have them share that same initial point. So u again is up 2, 1, 2, 3, 4 to the right. Negative v is up 3 to the left 2. And now build your parallelogram. So negative v comes over to here, positive u comes over to here, initial point to terminal point. There's my u minus v. So that's the graphical approach for your addition.